A little bit late. We got into another discussion. So, hello, Dr. Albers. How are you doing?
I'm very well. Thank you, Wayne. And you?
Good. Doing good. Doing good. Springtime is here in the Rockies.
Yeah.
So, yeah. So, good to see you. I just want to say hello to everyone in the chat room. Thank you, moderators. Thank you, Claudette, Kenneth, and wow, Deborah Tucker. So, it's already a full house. Well, 6 people left. Nope. Now there was 10 people come back in, so it's building. So how are you?
I'm well. Thank you. I'm very glad that spring has finally arrived 1 month late, but
well, let's hope it stays.
Yes.
And now the summers. Well, I guess you'll probably be looking forward to the summers. I know they get humid there in Pennsylvania, as I understand.
I don't mind humidity at all. You know, I was born in a country where humidity was extremely high, and I loved it. So I was born in Mozambique, tropical weather all year round.
That is. Wow, I did not realize that, Claudia.
Yeah.
Well, we actually have some questions from the audience. Would you like to, I send you a lot of them, and then but I thought this one was particularly interesting because I don't have an answer for this. So a person by the name of Appel writes, can you please ask Dr. Claudia Albers about the behavior of photons? My doubts are, 1, how, if the photon is massless, can it split in the presence of an electric field in 2 particles that have mass, an electron and a photon, and with different charges, positive and negative, and with different masses, MP and me?
Well, the thing is, it's energy. It's all energy. Mass is energy, and the photon has energy. All you get is a conversion from one form of energy to another. So you have the photon that has a certain frequency associated with its energy, and that is transformed into mass. And that is exactly according to Einstein's equation of E equals mc squared. It's nothing new there.
Okay. And he goes on to say, and also give to this 2-particle gravitational and electrostatic potential energy, the 2 characteristics, and I have to follow this more, and a total of 6 characteristics. I'm not sure what he's asking there, but maybe you do.
Well, I try to simplify everything that I say, and I start out with the photon that has an energy, no mass, and it splits into 2 particles. This is well known. This has been known for many years, that photons split into particles.
Right.
But up to now, they have always said that it's a particle-antiparticle. That does not mean that the particles don't have mass. What they are saying is that the particles will then annihilate. And what I've made different is I said there is no such thing as an antiparticle. And the reason for that is through observation. We are living in a particle, not an antiparticle universe. So how can we say that as many particles as antiparticles are always created when we're definitely living in a universe that's made out of particles? There isn't an equal number of particles and antiparticles in the universe.
Well, I've often had as we talk about, you and I have talked about antiparticles, antimatter, and you bring up a very salient point, and that is this, is that we live in a dimension, in a reality, in a universe that has specific laws where photons are concerned, even matter itself. And I'm not saying that it potentially does not exist, antimatter, antiprotons, etc. But what I'm saying, I agree with you. How could we observe it in this dimension? We wouldn't have any ability to see it.
Yeah, you see, these slight little things that are part of the standard model of particle physics are what is confusing people.
Mm-hmm.
It's not that you have a particle with mass and a particle that has negative mass. It's not negative mass. Both particles have mass, but they have opposite charge. And what we see is photons turn into two particles that have the same mass, but they have a tendency to collide again and annihilate. And I explain that in my article, saying that when we have two particles of the same mass, then the gravitational attraction and the gravitational repulsion is the same. So the electrostatic interaction in that case will bring them together again and they will annihilate. It's only when you have particles that come out of it with different mass, that is the proton and the electron, that the tendency to separate from each other is not of the same strength as the tendency to attract each other.
Well, that was one thing I had difficulty overcoming, was the annihilation theory. Because if they say that, if a positive and anti meet, that there's an annihilation that happens, but it seems like then that would be just an absolute, but apparently that's not the case. He has a second part to this, Claudia. He says, all right, so when the photon splits, whose force prevails? The gravitational force that is weak or the electrostatic that is stronger? And he goes on to say, if it's the electrostatic force prevails on the photons and electrons, you just said it, will get together again. And that's exactly what you said would happen with the electrostatic force.
That's right. So what happens is it's dependent on the initial energy of the photon, because the initial energy of the photon goes into creating the mass of the particles, and then there should be some energy left, which then exists within the particles. And this is photons. We know that photons exist within particles because when we have an atom, and the photon comes in and is absorbed by an electron, the electron moves to a higher orbit or exits the atom. So we know the photon got absorbed by the electron and therefore is inside the electron. And when that happens, the gravitational energy of the electron increases. So its repulsion to the protons that are in the nucleus increases, and that's why it moves to a higher orbit.
Interesting.
Again, this is built on observation as well. This is what we observe all the time. This is how photons are absorbed by matter, and why when electrons move to a lower orbit, what happens is a photon is given off. This is why atoms then give off light when they move to their lower energy or the ground state. They give off a photon. The photon was inside the electron and is given off.
Well, it's interesting because he goes into, this is a very long multi-part question, because he goes to number 3. How is it possible that once the photon splits, part of the photon remains in the particle that was just formed and remains with all their potential properties? Is it divisible?
Well, like I said before, we know that photons exist within particles because of what happens with atoms. And I had to realize as well that the gravitational interaction has to be of different strengths depending not only on the mass of the particles, but something else that causes stars to have different degrees of charge separation within them. So planets, I realize that planets and stars are the same thing. But if a planet is larger, then there's more gravitational energy within its particles. And that gravitational energy causes the proton and the electron to separate from each other. And that's what causes the potential difference between the core and the outer layer. Then that's what causes the discharges, and that's what causes then the atmosphere of that star to be able to give off light through these discharges. So it was all due to the fact that there has to be a separation force, which I then realized it had to be part of the gravitational interaction. It's just that the separation was between protons and electrons. And then I had to realize, okay, but then the protons must attract each other. And that's actually the strong force. The gravitational force that we feel is actually the strong force, but at longer distances. So at short distances, we get the strong force, which is what causes fusion to occur, what causes protons to come together and neutrons to come together, because the main part of a neutron is still a proton. And so they will still be attracted under the strong force to other protons. So that's what causes nuclei, heavy nuclei, to form. It's the strong force. It's what causes the nucleus to stay together. And then at longer distances, you have protons in one nucleus here, protons in another nucleus there. What attracts them to each other? It's the same force, but it's now at a longer range, so the force is not as strong. And as the range decreases, it doesn't decrease in a linear fashion. Eventually, what we get is one celestial body here, another celestial body there. And what attracts one to the other is the protons in their cores. Well, this guy, each other. That's the gravitational attraction between protons. That's what gravity is.
Okay. By the way, Carlos is his name, and he's from Argentina. And
okay.
He said he is with
Those are
a group,
good questions,
and they are amateurs in physics. So I'll read his next question.
Okay.
If the photons don't meet with an electric field or collide with an object, will it travel eternally without losing its properties? And you just about described it, I think, in the effect of what gravity does.
Yeah, that's right. The photon is a particle that will keep on traveling at the speed of light forever unless it's absorbed by matter or unless it goes through a region of high electric field, and then it will split.
Because he answers, the next question is, the matter creation only happens in the presence of an electrical field, or also when a photon collides into a wall, or when it interacts in the photosynthesis. It's like you're reading these questions, and folks, she can't see this.
So I never even thought of the photosynthesis, but that's there's some differences in photosynthesis.
Okay.
Because there the photon, there is and there isn't. There, what we have is a chemical reaction where the photon is absorbed by electrons.
And that's a unique aspect, as opposed to saying a photon hitting the Earth, the Earth's atmosphere, et cetera, going through. Because there's another question later about neutrinos someone wanted to ask you about. Okay. So how I see this as a layman, and if these guys are amateurs, then I'm a newbie because I really am. But when I see photosynthesis, what I'm seeing is just that. I'm seeing a photon actually being able to be manifested in a chemical equation.
Yes, it's a chemical reaction, definitely. And when we're talking about chemical reactions, we are talking about atoms interacting through their outer electrons. It does not affect the nucleus.
He said, how is its energy neutralized?
The energy of a photon.
I think that's what he's asking. Yeah.
The thing is, you don't neutralize energy. Energy is always conserved. It transforms from one form to another. It starts out as a photon. It may transform into mass. It may transform into a neutrino, but it doesn't get neutralized. In other words, it doesn't die, so to speak.
Well, that's kind of the principle of, is it the second law of thermodynamics, that energy is neither created nor destroyed, but is in a constant state of change?
Yes.
You see? All right, let's go on.
Energy is conserved in the universe.
Exactly, and that is the fourth state. The fourth principle is conservation of energy, correct?
That's right.
And that kind of goes to his next question. How can the photon stop its enormous speed suddenly? Will it disappear after a collision?
The thing is, what happens to the photon when it gets split, it's because everything is a resonance. A photon is a particle and it's a resonant in space. And it's a resonance that's moving through space at the speed of light, but yet it's spread out through the whole universe because it's a wave function. It's a wave.
Yes.
So whenever you have a resonance, you have resonances within resonances. So the particles are in there already, but they're not manifested as mass yet.
Well, that's the whole experiment as well, is that a photon can be both a particle and a wave, correct? It just
Exactly.
depends on
Everything is both a particle and a wave.
You see, and Claudia, this is where I'd love to be able to be in a classroom, actually, because here's the thing that I question is that we can observe a photon in a state, basically, I call it a flux state. We can see it either as a particle or as a wave. I can't help but not think that there is a courtier between those two states that I think holds a whole lot of new opportunity in the world of physics.
Mm-hmm. Yeah, it's basically we would go into quantum mechanics, and that's how the universe is described. You can choose. The thing is, it's difficult for our minds to conceive that both are there at the same time. So we like to think of, okay, let's treat it as a wave for now, or let's treat it as a particle for now, but it's both all exist at the same time, at the same place. A wave has particle properties, and a particle has wave properties. They both are one in a sense, but we find it difficult to conceive of them being one and the same thing.
Yeah, is it two separate equations?
Separate.
Is that what we're dealing with here? Is it the fact that we're trying to define this into two separate equations that if you go off, for instance, in the wave path, that as you develop the form, your math to it, whatever it is that you're trying to do, that's not able to be transposed over into the particle, right? Or is it?
It is in a way, but it just conceptually, it's difficult to
I can imagine.
Think of it.
I can imagine. His
but
last question.
Basically, what it is that the particles are inside the photon already as waves, as resonances. When it goes through the electromagnetic field, because you have the two particles that are dependent on the energy of the photon. So a certain photon will have certain possibilities for what particles it has inside it. So at the moment, if at the moment the photon is in the proton-electron resonance, as it goes through the electric field, what happens? The proton moves in one direction and the electron in the other, because inside an electric field, a proton will always move in the direction of the arrow and the electron in the opposite direction.
You know, when you talk like when you describe the equation, I keep on seeing within a photon the equation of unlimited unrecognized potential. Mm-hmm. It's almost like a stem cell. It depends on what you want to put it in, but it has the ability yet to exist. Last question he has: if the theory of the matter creation through light is real, what happened with the light that hit the Earth in the surface and in the inner core? It had to produce a lot of matter in the last billion years. As you can see, I have many questions.
Okay, so the thing is, what actually happens is for particle creation to occur, you need an extremely high electric field.
Okay.
That's usually not created much within planets. I mean, it usually happens when you have these huge electric discharges. And the way stars form is due to the electric discharges that occur from the galactic nucleus. So what happens is at the galactic nucleus, this is where stars really form. At the surface of the galactic nucleus, just like on the surface of a star, there's a huge electric field due to the huge difference between the interior. The galactic nucleus, like a star, except it's much larger, has a nucleus. And that nucleus is positively charged, and out the edge, it's negatively charged. Between the two, there's a huge field, a huge electric potential, and huge discharges are occurring. When these discharges occur, what we have is photons being given off due to the discharges. Again, it's energy transformation. And because it's in this region of very high electric field, what happens is the photon suddenly splits into particles, but the field is so intense and the heat and the energy that what you start occurring is fusion occurs almost immediately, and a whole lot of heavy nuclei form. Everything that's in the periodic table and beyond the periodic table, huge number of unstable nuclei suddenly are formed from just photons splitting. So then the gravitational attraction starts bringing the nuclei together, and what you get is the nucleus of a new star forming. This is where it's occurring. And then it's flung out into space, and the galactic nucleus is rotating, so it's flung out into space into it's an elliptical orbit around the galaxy. The galactic nucleus, then the galaxy rotates a little bit more and ejects more. And that's how the spiral arms of the galaxy form. That's why they form spirals, because the stars that form at the galactic nucleus are going out in an elliptical orbit. They're going around, and then the galaxy is turning and creating more as you go along. And then that creates this.
You know what always amazes me?
Going around like this
is the fact that when I think about energy, whether it's on a galactic cell or if it's like an explosion that we can see the Bow-shock wave, that in the universe, everything is round. Yeah. Everything, we don't see squares, right angles. Everything is round.
Yes, and that is due to the magnetic field, the magnetic interaction. Because when I did all this, I simplified it and I just said, okay, I'm going to talk about the electric and the gravitational, because I can explain all the structure that's happening in the universe. Basically, the universe, all matter and energy in the universe is contained within photons.
Light.
We are living in a universe made out of light. Everything comes out of light. And the interactions themselves come out of the photons when the particles emerge.
Can I ask you something? When we talk about light, and because as you're talking, I'm seeing in my mind a visual of the universe. How is there a limited amount of photons? Because it seems like to me that if photons were the primer of everything, where would we get all this darkness from? Because it seems like the darkness is the absorber of a photon.
No, the darkness is just where there are no photons coming from that direction.
Ooh,
or at least no photons that we can detect. There most likely are photons there, but in other wavelengths that we do not see.
That's that part of the Sagittarius dwarf galaxy that we're seeing, that it's basically no light, and we can't figure out why.
Yeah, well, that could be two reasons, either because there's something between us and that region of the galaxy where there is that's absorbing the light, or it could be that all the stars in that region have died. And therefore they're not in the
What do you think about that? a dead spot in the galaxy.
Well, we have dead stars in the
Sure.
sun's corona, huge numbers of them. So we know it's possible that we could have a whole region inside a galaxy where all the stars have died.
Well, as you were saying that, it's interesting. Okay, I'd like to carry this further in another episode because I'd like to talk about more the fact that if a light, there would be something in I'm a thinker and I'm just expanding here, Claudia, is the fact that if darkness can exist in the same universe that light does, do we have two opposing forces in which is greater? The darkness, does it absorb the photon, or is the photon greater than the darkness? I don't know.
The photon will always overcome darkness as long as it can get to that region of space. Basically, darkness is absence of light.
Mm-hmm.
And the moment light reaches that region of space, the darkness is overcome. All it has to do is reach it. So we don't have darkness coming in and overcoming the light. The light always goes and overcomes the darkness.
Claudia, do you think we've yet to discover another form of light? I keep on thinking that what we see is merely in the white shift of light. That's the white rays. Mm-hmm. That's what we define as light. Something keeps bugging me and telling me, and I know it's theoretically it's impossible, but something tells me there may be yet something of a form of light or another light that we're not comprehending. I don't know. I could be.
Well, that's always a possibility. The light spectrum has no limit at the top or the bottom part. At the top part, we have gamma rays, and there is no limit to what wavelength or what frequency gamma rays can have. There's no limit. We can go up to infinity. And at the bottom, we have the radio waves, we have long waves, and we can have waves that are as long as infinity. So there is no limit. Basically, everything that we could possibly encounter is in the spectrum. It's just we don't usually encounter long waves that are longer than a certain amount, and we don't usually encounter gamma rays that have a higher frequency than a certain amount.
Well, it's great theory, and I'll still ponder it, send it to you. So you actually did some papers this week, and I just thought that if you have a chance, let's talk about this one.
Okay.
Okay,
that's about neutrinos.
Yes, because you know what? On my list, someone had already sent in. So it's the synchronicity. It's crazy, folks. Mm-hmm. Okay, Dr. Albers, so I'll let you take over.
Yes, thanks. So why I came up with neutrinos is because the stellar cores have energy, the outside layer of material which they shed when they come into the sun's corona. And here I talk about the objects that are drawing matter from the sun. I just do my little introduction because I know always get people watching the video that have never, heard anything. So I always have to do some kind of introduction to get them started. So here I explain again how the photon splits into protons and electrons. Okay. And why do I always maintain the proton and the electron? Because of the universe we're living in. Do we have protons and antiprotons all over the place? Do we have eta hadrons anywhere? We do not. We have protons and electrons. That's what the universe is made out of. So we know that this reaction is what predominates. Photons turning into protons and electrons.
Okay.
Because that's the universe we're living in. And then I explain again about the two interactions, which is the electrostatic and the gravitational, which always play against each other. They oppose each other. And through these two interactions, we can explain just about everything that goes on in the universe. The only thing that's missing is the fact that everything is rotating, and that has to come from the magnetic force, which always causes everything to move in a circle.
This electrostatic interaction is a new one, I think, for a lot of people, trying to balance that with gravity.
Yeah, well, the electrostatic interaction is actually the one that should be well known to people. That's what causes electricity to flow in wires. That's what causes you to be shocked in winter when you touch a metal surface, because you have extra charges in your body. Or
kiss your wife.
And when you touch something, they flow out of you to ground. It's the electrostatic interaction that causes two like charges to repel. That's why the two protons repel, because they have a charge of plus E. So they repel, whilst the proton and the electron attract. But why I started this is because I observed, and just stop there a moment.
Okay.
Here I explained that what powers stars in the interior is fission. Because remember, I said that whenever a star forms from this huge electric discharge, when a whole lot of photons are emitted and then split into particles, and then heavy nuclei form, some of them are unstable, and then they combine into a nucleus. So what you have a nucleus full of unstable nuclei. And what are they going to do for the next billion years? They're going to fission. Mm-hmm. And they're going to give off energy. And this energy can be described in two ways: heat or gravitational energy. Whatever, it's light. It's light. Why is the Earth even heated by the sun? It's not like the sun actually touches the Earth. What we get is photons coming from the sun that heat the surface of the Earth. Heat is photons, and photons are gravitational energy. So gravitational energy is heat. And the photon within the particle causes the particle to vibrate. And the more photons are in there, more photon energy, the more it vibrates. That's heat. And that means that, but heat, it always flows across material. So if you touch two protons, if they collide, they share whatever heat they have in them. So that means that if one has more photon energy than the other, when they collide, it gets shared so that they have the same amount.
So the positive charges.
That's how I know that photons flow from one particle to another just when they collide. It's shared equally.
Okay.
But the stellar cores, the outer material is very low in gravitational energy. It's so low that the gravitational interaction they can have with other stars or other planets is zero. That's why the material just floats around the sun. Gravitational interaction, zero. The sun exerts no force on them whatsoever. They just float around the sun. If they had any ability to interact gravitationally with the sun will pull them in. It doesn't. It just floats around.
Interesting.
But the stellar cores are able to pull matter from the sun. So they have some gravitational energy within them that did not get shared all the way across the object. So that means there's a form of gravitational energy that does not get shared, and therefore is not in the photon form. And this is what happens to stellar cores, what we see here. When an electron and a proton combines to form a neutron, that's because the two particles have low gravitational energy. So the separation interaction is not strong enough, and the electrostatic takes over. And now they are attracted to each other and they collapse into a neutron. When that occurs, because the neutron is actually more massive than the proton and the electron together, it means that some of the gravitational energy, whatever was left in there, gets transformed into mass when that reaction occurs. So that again shows me that they were so low in gravitational energy, but yet there's still some gravitational energy in there. So what is that gravitational energy? It is what we see whenever an electron and a proton combine. What else is given off? It's a neutrino. So when we have the two particles combining, one particle emerges, whatever else is supposed to emerge, it's usually a photon or gamma ray. It's usually energy in the form of a photon. But now, instead of a photon, we have a neutrino. So what does that mean? The neutrino is energy like the photon, but in a slightly different form that doesn't get shared across the particles. In other words, what I realized is the photon energy that's initially there. When the particles split, some of it exists as photons within the particles, as heat, and some of it exists as a neutrino. There are neutrinos within particles.
What are the characteristics, the properties of a neutrino?
A neutrino is a very unreactive particle. And it's very strange. It doesn't react with matter at all. It goes right through matter most of the time. So it's very difficult to capture a neutrino. But it can react with heavy water, but very few reactions occur.
Claudia, isn't the French that has the experiment? And I'm trying to get this right. They have a tunnel that they have drilled a hole down, and I think it's a mile or something. They filled it with water to try to capture a neutrino, correct?
That's right. They have to isolate the tanks so that it produces a little, when it reacts with the proton in the water, it releases a photon. It's a blue photon. And they detect that photon. That's the way they detect a neutrino reaction or a neutrino being captured by matter. But they have to eliminate all other possibilities. So they have to eliminate all other particles that may cause that light to be emitted. They have to make sure that it comes from a neutrino. So they usually put it deep underground. Put the tanks deep underground so that there is no confusion. It has to be a neutrino that was captured.
This seems like a whole new exciting area of research. Okay, so I'll let you go on. I just want to know what a neutrino was so everyone else knew.
Yeah, and the thing is, the neutrino, why it's so peculiar is that it sometimes seems to have mass and sometimes it doesn't.
I love that.
Yeah, so what that means is that it's a type of particle that can transform part of its energy into mass.
It must be a Gemini. I'm just kidding. All right, you got a little philosopher humor in here, folks. Deal with it.
It still comes out of the photon. I sometimes call it a photon with mass.
Yeah.
It still comes, all particles, all energy comes from the photon. But basically it means it's a photon in a new form. And it's in a form that's what's left inside the stellar cores. That's the form of gravitational energy they are left with. After billions of years of giving off light, basically they gave off all their gravitational energy. And all that's left is neutrinos. And that's the neutrinos in the core. In the outer layer, even the neutrino energy has been given off, possibly as they combine to form neutrons.
Does a neutrino has mass then, correct?
Sometimes it seems to have mass, sometimes it seems not to have mass.
Ooh.
That's the strange thing about it. Also, it's difficult to actually calculate its mass because it's a particle with no charge, so it doesn't produce any...
a particle with no charge.
Any trajectories, in the cloud chambers from which we could calculate its mass. It doesn't.
With no charge, boy.
It's a neutral particle.
Yeah.
So,
you know what? These hours are just great. So we have here, I'll let you go on. This is just exciting.
This is where I show what happens to the stellar cores. Basically, we have a stellar core there. This is a cactus image. This is a CME, and usually they are found within CMEs. Why? Because they actually provoke the sun into having CMEs as they pull matter from the sun. Eventually, they pull so much matter that the charge separation part of the gravitational interaction takes over, and it ejects it because it's repelled by the sun's outer negative layer. And at the same time, all that matter that it was drawing is ejected as well, and that will look like a CME.
So I see a dark area here.
Yeah, but there seems to be there's a large circular outline, and then there is that dark region over there. It may be more than one. They are known to cluster, and sometimes we get more than one together. But we also see the CME material going across it.
Yeah, look at this.
It's actually captured some of that.
Look at that.
But what I'm really interested in is those little black and white specks. Do you see those black and white specks?
Here?
Yes, all over the image?
Yes. Yep.
Now, those are the clumps of matter, the debris that comes from the outer layers of the stellar cores. They shed that outer layer when they come into the sun's corona. And these specks of matter just float around the sun. You can actually see them moving whenever the sun releases a CME, as if they've been buffeted by wind. Basically, they are impacted by the particles themselves that come from the sun, and that's what causes them to move.
Are they attracted to the sun, or is it just...
They're not. If the sun is not having a CME, they just float around.
How odd.
Nothing happens to them.
Well, this goes in line with something okay, all right, I can dig this.
So this means they have no gravitational energy because the strength of the interaction they have with the sun is zero. This means that G, the gravitational constant for the interaction between these particles and all other matter, is zero. They have mass, they can have mass, but the gravitational constant is zero. What determines the strength of the gravitational interaction? Zero. So that means there's no attraction. The attractive force is zero.
Would they be absorbing heat that close, or would it?
They would be able to absorb photons if it was possible for them to do so. The fact that they seem to just float around and do nothing seems to suggest to me that they have gone even beyond the point where they can even absorb photons. Wow. And this is possibly why the stellar cores, they shed them. They can do nothing with them. They absorb new matter from the sun that is high in gravitational energy, and they shed all their outer layer, all their ionizing layers, their outer envelopes, and they form new ones.
Claudia, we ought to talk. As you were talking, now this is the entrepreneur of me. If it was possible to capture something like this, could you imagine the new material, the new sciences that would come from this? It would be revolutionary.
This is the thing, Wayne. Through observing the stellar cores, I have basically rewritten physics.
Oh, yeah. I know some people, this is, wow. Okay. All right. I'll let you go on, Doctor. My mind's going.
The thing is, they have been blocking us from understanding this for many, many years. Notice that whoever, and James McKinney talked about this, that whoever started talking about electric fields in space lost their job. He lost his because of it. It's all because starting to understand that there are electric fields in space would lead you to understand what's actually going on, how gravity really works, like it has led me to that understanding. And I have James McKinney to thank for a lot that I have started understanding about gravity. Without his book and his description of what he observed, because he was at a university as this data came in the 1970s and so on, I would never have been able to come up with what I have about gravity.
I find this statement right here revolutionary. The neutron is more massive than the proton and the electron. I mean, this is fascinating.
Yes. The neutron has slightly more mass than the proton and the electron. That means that whenever that reaction takes place, some gravitational energy is converted to mass energy.
What's the equation? Can you help us out on this one?
The plus is a proton.
Okay, proton.
The plus means it's positively charged. The P stands for proton. The E minus is an electron. Okay, the word electron starts with an E. The minus means it has one negative charge. The arrow means, okay, it turns into N. N is for neutron, plus the mu E, that's the symbol for a neutrino, an electron neutrino. You get neutrinos that are associated with electron reactions, and you get neutrinos that are associated with muon reactions and with the tau meson as well. So you get three types of neutrinos. But here I just concentrate on the electron neutrino. I don't want to complicate things.
Yes, trust me, I appreciate that. I mean, I'll admit it. So, all right. Go on, yeah. Doctor.
So then, this is why I realized what neutrinos are. Neutrinos are carriers of gravitational energy as well. But it's not in the form of heat or photon that just gets shared across particles. It means that particles collide, their photon energy gets shared, but whatever neutrino energy they have within stays within the particles, doesn't get shared.
That's okay.
But it still contributes to the gravitational interaction. That's why I call all this energy gravitational energy, because it goes into defining the strength of the gravitational interaction. So here I summarize the three forms that we have of gravitational energy: the photon itself, from which everything comes, and then and the fact that it exists as free photons and it exists as energy within particles. Okay, I do describe those two under the first point there. And then there's mass energy, which exists as particles with mass. And then there's neutrino energy, which is a type of photon with very low reactive ability, which may at times manifest its energy may manifest partly as mass energy. And there's one of the dark stellar cores. These dark ones, they're dark because they're absorbing all the photons that are impacting them. They're absorbing gravitational energy in the form of photons. And this one is making its vortex connection or plasma connection with the sun. So it's absorbing matter as well. And it's absorbing gravitational energy that's within that matter through that. So it's absorbing energy in two forms: photon and matter.
Wow.
Yes. And these dark ones, that's what they're doing. They're absorbing a lot of photon. So they possibly new arrivals that don't have enough gravitational energy to do the charge separation thing that all stars do yet. Eventually we'll get to the point we'll start being able to do that, and then you'll start being able to emit some light. And here's one of these large ones. Here I indicate that stellar cores are likely to expand as they age, because the gravitational energy decreases as they age. And that means that the attraction that the protons have for each other will decrease. And when that happens, the star will expand in size, because the protons won't be as attracted to each other as before. So that's possibly why we have such huge big objects. This one is as large as the sun. This one there.
This is the sun right here.
Yeah, the sun, the white circle gives you the size of the sun. And that huge big one is about the same size.
Look, it's huge.
It is huge. But you can see it's not interacting with the sun gravitationally as it should. If it did, if we had two suns next to each other, what do you expect them to do? They would just collide.
Right.
This doesn't happen because they are so low in gravitational energy that the interaction they have with the sun is extremely weak. I calculated that it's about 0.06% of what it would have been if they had the same amount of gravitational energy as the sun. But here we have one that's emitting light because we can see it has stripes.
Right here, right?
Yeah.
Actually,
so this is not an object that it would look dark like the other ones in the sun's corona if it wasn't emitting light. This one has actually stripes and it's emitting light. So it's absorbed enough energy. Either it's absorbed now enough gravitational energy, it's also pulling a lot more matter from the sun than those little, the black ones can do. They just draw a little vortex. This one is, you can see a whole lot of material being drawn behind it.
Right through here. Yeah.
That's
you could hear different light
and
spectrum.
It has stripes and the stripes curve around the object showing that it's curved, it's a sphere, but it must be emitting light. So it must have a lot more gravitational energy than the black ones. So either some of them are getting to the sun that still have some gravitational energy, but I doubt that because then they wouldn't come to the sun and be in the sun's corona like these ones are. I think what's happened is they possibly gain gravitational energy with time and eventually start being able to emit light, and they start pulling more matter from the sun. So that showed me that as they spend more time in the sun, their effect on the sun will increase.
You know, I was just looking at this compared to the Earth. It's just, what is that? It's about 1.5 times the size of the Earth right here?
This one is about 4 times the size of Earth. It's quite a small one.
Yeah.
In comparison
by the way,
to others.
I know the detractors of Nibiru and Nemesis. Someone wanted me to ask you, do you think that Nibiru is actually rotating around Nemesis? You can answer that if you care, but what I'm trying to...
I have no data to be able to tell you
Exactly.
that.
Yeah, that's what...
I have no data. I cannot speculate about this.
Yeah.
Unless I have... And one image is not going to tell me anything.
Thank you.
It's got to be tracked. It's got to be seen more than once. It's got to be compared.
That's what the deal is. Exactly.
We cannot mix fables and myths with actual observation. We observe stellar cores in the sun, and I go along with Terrell in a way because he is able to track this object through earthquakes, about the black star. But even then, I have no real data. I have some evidence that it is likely to be an object that's not a stellar core, that's interacting with the sun as if it has still gravitational energy and interacting gravitationally with the sun. It seems to be coming in, and that's possibly what's causing our magnetopause reversals at times. Okay, so I have that evidence, and then I talked to Terrell. But it's still iffy because I haven't actually observed the object. It may not be possible to observe it.
Well, it's like this. As we found out this morning with another asteroid that passed in between us and the moon, we did not know about this object until literally 24 hours ago.
That's right.
And that is just how quick. And here's my thought on this. When people try to get so wrapped around the axle on this, my attitude is this: we don't know. Who knows? Maybe one day we wake up and we get a mass world alert that something's out there. We know something's out there. We know that what I have come to the conclusion is this, Claudia, we're still discovering. We don't know everything.
That's right. We do the best we can with what we have. But there's a point where I just cannot speculate. And giving, I call these objects Planet X in a way to honor Dr. Robert Harrington, because he lost his life because of what he found.
He did.
And he called it Planet X. And the thing is, we don't know what it is. There's something there. And he obviously found something, or they would not have killed him. And
there's been others behind him, by the way, that have met an early demise. Yes,
he's not the only one.
Right.
It's true.
The Kuiper Belt is big. I don't think people realize this. Another thing, Dr. Albers, the thing that I keep on the article that they said that diamonds are now raining down on the Earth, and they've tracked it back to the asteroid belt, which again, that was a planet. No one talks about that planet.
Yeah, that's likely to have been a planet. That's right.
And I read an article over the weekend that said it was in the habitable zone.
Yeah.
Yeah, exactly. And I went, oh, yeah. So,
yeah,
anyway.
And it shows that the accretion form of planetary system formation doesn't work.
Yes. But who am I?
Why didn't all these asteroids combine into a planet?
Well, now you're going to get technical on us. Well, I'll let you continue on this because I know we're almost...
Yeah, okay. And then there's the other thing that I discovered, that the Earth must have captured some stellar core material. Some small stellar cores have been captured by the Earth. Basically, they've been attracted to the Earth because the Earth, even though it's a small planet, it generates gravitational energy within its core. There's fission going on within the Earth's core, just like there is within stars. It's just that it's a lot smaller. So, of course, it attracts the stellar cores as well. And so this is why I believe we have these ocean recession events, because the stellar cores are interacting with the Earth. They are coming very close to the atmosphere. They may even be coming into the upper atmosphere, just like they do with the sun. And they are pulling material off our planet. They are pulling atmosphere off our planet. They are causing these tides, very high tides, that then give rise to these ocean recession events. They are causing sinkholes. They are breaking up our planet. And then I say that because these effects are likely to increase because they gain gravitational energy with time. And then the gravitational effects will increase. In other words, this planet is going to go through a very bad time.
When I saw your picture here, I was not aware that this was up in the Aleutians. This is Alaska.
This is actually, it's close, but it's in the Russian part.
Yeah. And while this was going on, and I want to do it, but I'm almost betting that at the same general time over in North Carolina, they were experiencing the same effect. Claudia,
I'm not surprised.
This tells me that things are getting like this. I mean, if the Earth is a piece of saltwater taffy, we are pulling the daylights out of it.
Yeah.
More and more of this.
This is Africa. This is the Rift Valley in Africa. When I was in school, I learned about the Rift Valley. I said, we take 100 million years for this thing to open up and the ocean to go through. It's happening in matters. It's opening up in regions over a matter of days. This one opened up overnight. Huge, big rifts just opening up. They're supposed to take millions of years to form.
It's going pretty quick, if you ask me. Remarkably fast.
Exactly. Most geologists will tell you that it's impossible for this to be happening, and it is happening. It's happening because the Earth is going through a slowly developing cataclysmic event. That's what's occurring. This happened before, 4,000 years ago, when mountains just rose up, when canyons just opened up. This has happened before, but whenever there's a cataclysm or a comet comes by or something like that, we have this happening to our planet, but it's a slowly developing cataclysmic event. In a way, it's worse because it's not something that happens and then it stops. It's slowly getting worse. And there's no reason why it should ever get better.
Mm. I happen to agree. I mean, all the evidence is here. Wow. Okay. I don't know about you, but I have loved this. This is, Clyde, this is just great. And apparently we got a full room in here as well.
That's good.
Yeah, it's just.
Yeah, someone asked me a question today about why the sun is tilted at 6 degrees to the rest of the planets. And basically, that just shows that the accepted theory of planetary system formation is wrong. Basically, the sun and the planets formed from possibly from the same mass creation event from the nucleus of a galaxy. Either that or the planets were captured, but they were all separate entities. They were not created from the same cloud. And they came together into one system. And that's what it shows. That's why the sun is tilted at some degrees to the other planets. That's why.
So I wrote this over the weekend. You didn't even see that. I wasn't even going to bring it up.
Okay.
And I wrote and I said, could man have gotten it wrong in determining the universe of what is up and what is down?
Well, basically,
I mean, what is north? How did so? Okay, I'll let you go. Are we taking north because it's north on Earth?
Yeah, I mean, we see it from our point of view. We see everything from our point of view, but we have to define a point of view. And it's usually defined in astronomy as, okay, the celestial plane. And we say, okay, the north pole of the sun is the northern hemisphere above the ecliptic. It's all defined according to some way that all the astronomers have agreed on.
Okay, that helps because I'm still going. So really, that's what I asked myself. So one guy goes and says, well, that's the galactic plane. So everything, I don't know.
I mean, we can choose the galactic plane to define all directions and up and down as well. But we have chosen to use the plane, the ecliptic plane, which is defined by the plane in which the Earth is orbiting around the sun.
And
Most of the time we use that. There are some other ones that we can use.
Because I'm still trying to figure out if an astronaut's upside down and the other guy's right side up, but who's upside down? I don't know.
Yeah.
Well, another hour has zoomed by, Dr. Albers. I'll tell you, I love this. And I just want to say, I sing your praises all the time, but if people really want to come and learn science, this is every Monday when we're here. This is an opportunity for them to get an education that otherwise would cost them a great deal of money. And
that's good.
I just thank you. It's
a pleasure. I enjoy teaching and talking about my theories and what I've learned through observation.
Yep. And
my theories are all based on what I have observed.
Hi, Jeff. The point is this. And as I tell all the detractors that try to, and they're going away, I have to say this community is either getting them their heads straight or they're moving on. It's theory. And all knowledge arrives from theory. Mm-hmm. All theory is knowledge. It's just that we have to figure out which one it is, which one actually, as you said, by observation. And if I'm correct, Dr. Albers, in order to begin to establish something, it has to be able to be repeatedly observed. Correct?
That's right. I mean, you can observe something once, and all that does is it forms a question in your mind. Then you observe it again. And then you start to realize, okay, but there's something here. There's something going on. And that's when you start figuring out, okay, I've observed a real effect. Now, let me try and explain it.
Mm.
And then you try to get more observations that corroborate that effect, but they are in different circumstances, so that you can get a good picture of what's really going on. And this is what I have done with the stellar cores. I've observed them, how they interact with the sun, what they are doing. I mean, and the data is not that much, but I've used what I've had to try and explain what is it that they are doing.
Well, Copernicus gave us the definition of the universe.
That's right.
And his observation was far less, and his evidence was far less.
That's right. And he got into big trouble for it.
Yes,
too.
he did. I think the cat down in there in Rome was wanting to have his head, which tells us something that, they've always suppressed the truth.
The truth is always suppressed.
It always is. And it's brilliant.
Sometimes it's the truth because of how it's suppressed.
And my dear, you certainly have the scars to prove it. There are those of great minds like yourself who have sacrificed far more than what most people would even be willing to contemplate. And I admire you for that, Claudia. I really do.
Thank you, Wayne.
Well, folks, keep the questions coming. We'll do our best to try to maybe at the front of each program get to your questions. And then, Claudia, I think that as the show is now developing, let the kind of the second half just be strictly classroom direction from you.
Okay.
Okay. I
Sounds
think that
good.
I think it is. It is good. So we can really come in here and really begin to benefit. I think with the knowledge.
I think it's great that people come here with questions.
They do, and I'm impressed. Many of them are over my head, and I'm going, okay.
Very good questions, yes.
We got smart people in here. Y'all very smart. And we love you. We appreciate you. And Dr. Albers, until we meet next week, please tell Scott hello. He's always welcome, as you know, and I'm sure he knows. And we'll see you next week. And I just want to say thank you to the moderators and to everyone who's come in. And thank you for the respect and the level of maturity. That's what I really love most about the people in this. And it's, we appreciate it as well. And Dr. Albers, again, thank you.
Thank you, Wayne.
Okay, everyone, we will see you. By the way, tomorrow night, I will be over on the Milky Way Weekly. I'm going to be a guest for him. So tune in over there. Let's see if we can boost him up a little bit. We like to make everyone. And over in your channel as well, because you do post videos during the week as well.
Yes, I do. I write my articles and then I make videos. Yeah.
And which leads me to, because people said, can we get a copy of them? Go over to her channel and you can actually hear her going through them.
Yeah, I'm thinking of putting, writing another book, actually using the last few articles I've written and putting them, in a book form. That seems to help people.
Yes.
So
I love the idea.
Do that soon.
Yeah, because a lot of people have been asking, and I said, well, you just have to ask Dr. Albers because I feel privileged. I've got a great library of your work.
Yes, you get them for free. We Scott actually started selling my articles at $10 a piece.
Well, I think it's well worth it when you go and look at it. I have some textbooks. I really do that I just recently got. Claudia, One of those suckers was $400 and something. And
Wow.
I'm going, well, what's in here? You know?
Yeah. Textbooks are expensive.
They are very expensive. And you go, okay. You know, it's like how many, you know, anyway.
There are some that cost $1,000.
Well, you know what? Knowledge. What was it? What was it the great philosopher said? All those who enter in, be prepared to pay the tuition. All right, folks, we appreciate everyone. We'll see you next week here on The Physicist and the Philosopher. Be kind to yourself, and we'll talk to you real soon. All right. Bye-bye, everyone.
Okay, bye.